Now, to me, they all seem quite reasonable, rigorous even, but there was one that was a bit more hand-wavy than the others. Maybe you spotted it, actually. It's at this point where I said, the finger pushing down on the lever, it requires the same force to hold up 0.5 kilogram mass over here and the 1 kilogram mass over here. That bit's true. But then I said something like, in other words, the experience of the finger is the same in both cases. There's nothing that the finger could do to distinguish whether it's a 0.5 kilogram mass or a 1 kilogram mass. It sounds plausible, and it seemed reasonable to me when I first started thinking about it. But at the same time, I can't think of any physical concept or idea that would justify it beyond physics intuition. So this seems like a reasonable candidate for where we went wrong and how we ended up getting more energy out than we put in. So although you need to apply the same force in this scenario that you do in this scenario, maybe it doesn't follow that the experience of, say, waggling the lever is the same for both scenarios. Well, brilliantly, that's something that we can test. So I set up this blind test. It's not double blind because I can't be bothered to do good experimental design, to be honest. But anyway, we dragged a few people in off the streets, and this is what we found out.
Oh, I would say, if I had to pick, this one wiggles easier.
Interesting. Pan down on that. There you go.
Did I get it right?
Get it
the dog
right.
also waggles.
Test subject number 2, Lucy Green.
Yeah, one is obviously harder.
Yeah, great.
Yeah.
Which
Oh,
one?
definitely this one.
Okay.
Yeah.
Pan down.
So if I hold them both, I can convince myself that's the same force.
Yeah.
But you're saying the next, like the movement's different.
Yeah. Once it becomes a dynamic system, it changes.
Ah.
Yeah.
That's cool.
I also tried the experiment, and so did my wife, and we had the same results. So that seems pretty conclusive. Everyone that conducted the experiment felt that it was easier to waggle the mass that was at the same distance from the pivot as their hand, and harder to waggle the mass that was half the mass but twice as far away from the pivot. But let's try and quantify easier to waggle. What does that mean? Well, I think it means two things. I think it means for a given force, the lever moves more rapidly when it's a 1 kilogram mass here than when it's a 0.5 kilogram mass here. In other words, the lever accelerates more rapidly for a given force. Or to put it another way, the smaller mass that's further away requires a larger force to get the same amount of acceleration. And so to bring all this back to the lever in space, what we find is that when we apply a force of 1 Newton over 1 meter, well, it takes longer in the case of the 0.5 kilogram that's twice as far from the pivot. In other words, it accelerates more slowly and the velocity at the end is lower than my intuition would have expected. To wrap it up mathematically, we can ask the question, well, how much slower will it be going? Well, we know that the energy must be 1 joule, and then you can derive what the velocity must be from that. But if we're trying to disprove the free energy hypothesis, we should probably prove that the 0.5 kilogram mass has a kinetic energy of 1 joule from a force perspective first, which is actually really easy. The key is to notice that the force on the 0.5 kilogram mass is half a Newton, because that's how mechanical advantage works. From the work equation, we get half a Newton times 2 meters is 1 joule. You then get the velocity by rearranging the kinetic energy equation. And when you do that, you find that